welcome back everybody. We are just back at the grinded stone with some more work problems that we started quite a while back. We finished talking about the volumes of solids of revolution, then we started talking about work. So this is the last video we're going to be doing on work. We've got two wonderful examples that are going to be a little bit more challenging than even the last one actually. And these are going to be some good work problems that if you are able to solve these, you will know you are good for these work examples. So these physical examples are going to be stuff that you would see in a physics, likely a physics mechanics course. That is where work is usually seen, although it is seen quite a bit in Calculus 3, but that is for another playlist. So we are going to be looking at some physical examples in this video, and we hope that you are ready for that. So this first example is from Stewart's calculus book. This is example 6.4, and it's example number 4. Also, here we have a force of 20 newtons stretches a spring from equilibrium at 7 centimeters to 12 centimeters. How much work is done stretching the spring to this new length? Give your answer in joules. Okay, so first thing that we need to clear up, the units of joules. So if I have joules, put this in SI units, is equal to, we have Newton meters. Okay, so if joules is Newton meters, then that means that we have centimeters in our problem statement. So we're going to need to make sure that we're wary of this because we want our final answer in joules. So we're going to need to transition these centimeters to meters at some point. The other thing that we want to look at is we want to look at the Hooke's law. So Hooke's law is for springs. So that says that F, our force, is equal to the spring force constant called K times X, our distance. So we can actually write our force as a function of X. So we have our force as a function of X is equal to the spring force constant times our displacement. Okay, so let's take a look at what our problem statement says. So we've got a spring here, right? And it goes, and then it goes a lot there, and then we're just going to draw the little bit that we're interested in. So we're going from 7 centimeters to 12. So we have equilibrium at 7 centimeters. So what does this tell me? When I'm at equilibrium, I'm going to make a new x-coordinate. So we're going to have our coordinate system. That's going to be our x direction. And we are going to set x equal to 0 when we're at 7 centimeters, since that's our equilibrium position. So our spring is here, right? And that's where it rests, and we have something at the end of it probably. It rests at x equals 0, which is really 7 centimeters away from the wall. So let's say that this is a wall, and here we have the other wall. And then here, let's say this is x equals 0, so we've got a lot of spring there, but we're stretching the spring out to 12 centimeters away from the wall, which is actually 5 centimeters away from the equilibrium point. So our spring is going to be here, and that's where our spring is going to be stretched out to, and that's going to go back. It's going to go boing, 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 and then we are going to have some spring action. So first, what I'd like to do is I'd like to do some dimensional analysis and also look at Hooke's law. As I said earlier, Hooke's law is f of x equals to kx. And now let's also try to find our spring force constant and do our dimensional analysis. So we have that our force at x is equal to 5. So when we're 5 away from when we are 5 units away from our equilibrium position, we're at 20 newtons of force. And we are going to put this into meters, so we have 0.05 meters times the spring force constant. We already know the value of f of 5, that's 20 newtons. And so that means that k is going to be equal to 20 divided by 0.05, which gives us our newtons per meter, and that gives us 400 newtons per meter, which is joules. Okay, so now we are ready to do some more analysis here. So now we have our force function. We have our function of force, and we also know where we are integrating. We're integrating between 0 and 5, so any integral that we want to make is going to be between 0 and 5. So that means that our work, which is equal to the integral between a and b of f of x ds, or f ds if we're working just in our normal formula, f ds, but we're going to make that equal to the integral between 0 and 5 of 400x dx. Okay, so now what we can do is we can evaluate this integral with the fundamental theorem of calculus. So that gives us the work being equal to 200 times x squared evaluated between 0 and 5. And that's going to give us 5,000 joules. So we have 5,000 joules to get us the force needed between our equilibrium point and our stretched endpoint. So now we can take a look at our second example. This is, again, from Stewart's calculus book. This is example number 33 from section 6.4, and we're doing part A. So this is something that's applicable to astrophysics, which is something that's really interesting. So we're going to be looking at Newtonian astrophysics, and this is going to be a really pretty analytical solution. We've been doing a lot of numerical solutions, but I think that the analytical ones are what really build our ability to do this really pure math. So let's say that Newton's law of gravitation, which I'm going to show below, shows the attraction between two masses, where r is the distance and g is the gravitational constant. These values are going to be just r and g. We will define those actual values in later videos. But the g is the gravitational constant. So we want to determine the work done by to move a body, or let's say like a planet or something, from r equals a to r equals b if the other point is fixed. Okay, so let's take a peek. So let's say that I have a planet here. Say there is a planet, and let's say here is a planet, but this is a fixed planet. So maybe this mass is really just inconsequential. This mass here is inconsequential to the mass that we have here. So we're going to have our distance between them being r. So that's our kind of distance variable. And we're going to have a point at A, and we're going to have a point at B. And I'm going to show an equation that displays the force in relation to the distance, so an f of x, if you will. And that is going to give us the ability to determine the work from r equals a to r equals b if this body is fixed. So this body is going to be moving in that direction, I would hope, and this body is going to be staying fixed at its point. Okay, so here is the universal law of gravitation. We have F is equal to the gravitational constant times the product of the two masses over r squared. Okay, so let's take a look at what we need to do. So this is really an f of r. This is a function of r. So f of r is equal to g times m1, m2 over r squared. Okay, so now we can, all that we need to do is we really just need to integrate this between a and b, and that gives us the work. So we have the work is equal to the force times the distance. Well, the force is already in as a function of distance, so we are all set there. So now all that's left is to find the work by integrating. So that gives us that the work is equal to the integral between a to b, and we are keeping the endpoints at a and b, of g times m1, m2 over r squared dr. That gives us, we can just pull out the gm1, m2 out of the equation, since those are inconsequential variables in this integration. This is gm1, m2, the integral from a to b of 1 over r squared dr. Now, 1 over r squared is an integral that you should always just remember. Don't go about just doing the product rule, or the reverse power rule here. It's probably going to be a waste of your time. It's best to just memorize that the integral of 1 over x squared with respect to x, or just maybe dx over x squared, is equal to negative 1 over x plus c. Okay, so that's going to give us g m1, m2 times negative 1 over r times evaluated between a and b. Okay, so that just gives us the work is equal to g m1, m2 times 1 over a minus 1 over b. And that is our final example for work. It was a great couple of examples, and I thought we had some fun along the way. So in the next video, we're going to be moving to our last topic in Unit 5, and that is the average value of a function. This is something that we're only going to be talking about for a pretty short amount of time, and then we will be moving on to Unit 6, which is the techniques of integration, which is, in my opinion, the best calculus unit. So look forward to that.